that's it. So basically, we integrate over S that function. Make sense?
Right.
Okay. So therefore, it always is p-dimensional.
Okay.
I don't know why would you.
Yeah, I was just wondering if you'd like integrate out. I mean, it'd be like integrating out some indices without integrating out the rest, or something weird like that, or no, it'd have to be.
Well,
yeah,
but then the first, yeah, I see what you say. Then you have to, basically, what you would do, you would somehow reduce the rank of the form. You would contract some of these indices, we say, with vectors, and what remains you could integrate.
Yeah.
But you'll get a p minus k form or something.
Yeah.
Make sense?
Yeah, that makes sense.
Okay, so that's the pullback and the integral. So the pullback is basically the chain rule. It just, you change the differentials. It's by replacing dx by du. That's it immediately gives it to you. Well, you see that this is antisymmetric and all that. That's why this is antisymmetric and all this. And so if you have an n form and you're integrating it in n space, say p is equal to n. If p is equal to n and you integrate over some, say, domain in Rn or something, and then what this will be, you have any idea? Well, if this is an n form, if p is equal to n, then all of these indices in increasing order are just 1 to n. There is only one combination, right? So if p is equal to n, then you basically get, right, what is this? So that is equal to, well, that sum is basically all for 1 n. There's just one component. And that depends on x and u. And then you have dx 1 by d 1 d. Well, it's just a change of variables. And you should get a determinant of that. Well, okay. Let me just try it and then I'll explain. So you'll get determinant dx by du d1 dun. So that's what you'll get determinant. Why is the determinant? Well, that's because if you have dx1 dxn and then you do it's basically a diffeomorphism. You're just changing variables from x to u. There are n of them. So you do dx1 by du I1 dxn by du In du I1. Okay, but this is all antisymmetric. Well, here you don't need to. So because this is antisymmetric, well, if you sum all of this, these things can be, by permuting indices, you could always bring it to this order, du, du1, n. Okay, and this one will give you exactly the determinant. If you remember the determinant of some matrix is equal to, well, let me write it this way. A1 I1 and N IN, and you get epsilon I1 IN, but this is the permutation tensor, the Levy-Civitas symbol, so it's +1, -1, or 0, right? So basically the product of these guys, so of course this is antisymmetric and all of this, it's the product of these guys with the coefficient equal to 1, if this is an even permutation of 1n and -1, if it's an odd permutation of -1. And that's exactly what is here, so that's why this will give you the determinant, and this will give you that. And you get a standard formula from calculus, multivariable calculus, how to change variables in that integral. So, and the last thing is Stokes theorem. Let me just tell you what this Stokes theorem. Say, well, in very simple terms, it basically says this. That's the Stokes theorem. Now I just need to explain what it means. It's a very, very general statement. It is true for all dimensions and all submanifolds and so on. So here, let's say alpha is, well, let's say P form. And, well, D alpha is, of course, well, let's say P minus 1 form. And S is a P-dimensional submanifold. For example, in Rn. So you have Rn, you have a P minus 1 form, you put it on, well, first you take the exterior derivative of it, you get the P form. So that is the P form. And you integrate it over P-dimensional submanifold, how I defined it before. You parameterize it and then you pull it back, and that's the definition. And then it turns out that it is equal to the integral of the form itself without the derivative. This is P minus 1 form, and that is the boundary of S, which is of course P minus 1 dimensional submanifold. Well, it doesn't have to be a submanifold. Let's say a piecewise submanifold. It could be consisting of. It could have corners, basically. But let's say in the simple case, suppose that it is smooth submanifold. So suppose that S is a P-dimensional submanifold with the boundary that is also submanifold, P minus 1 dimensional submanifold. Well, let's say